Hello everyone, welcome to Neso Academy. In the previous lecture, we have implemented the half adder using behavioral modeling. And in the fifth chapter, I have already explained you all three modeling styles: behavioral modeling, structural modeling, and data flow modeling, out of which we have already implemented the behavioral modeling style using the half adder in Vivado. And today, we will implement the same circuit of half adder using structural modeling, which is very important. So, our today's topic is half adder using structural modeling in Vivado using VHDL. Now, before implementing the structural modeling code for the half adder, let us quickly revise what is the half adder. In the previous lecture, we have already seen that the half adder is an adder that adds two single bit binary numbers without considering the input carry from the previous stage. So, half adder adds two single bit binary inputs A and B, and it generates two outputs, sum and carry. And these are the respective outputs for these four input combinations. Now, using this truth table, we have already constructed the logic diagram of the half adder, where sum is equal to A XOR B and carry is equal to A and B. So, we will implement this half adder using structural modeling in Vivado. Now, what is structural modeling? Structural modeling describes the components, how they are connected together to create the entire structure. Now here in half adder we can clearly see that this circuit is made using two components or two logic gates, one XOR gate and one AND gate. So in Vivado, we will write the VHDL code for the XOR gate and AND gate separately and then combine them together using port mapping to create the half adder. So let's implement the half adder using structural modeling in Vivado. So we are in Vivado and this is our Vivado dashboard. To implement the half adder using structural modeling, we need to add two source files, one for XOR gate and one for AND gate. And then we need to write their VHDL code in these source files. First, let me add a source file for the XOR gate. For that, go to Flow Navigator and click on Add Sources. Now, let me click on Add Sources. Then click on Next to create a design source file. Now click on Create File to create our design source file. File type as VHDL because we are writing a VHDL code. Then file name. I am naming this file as XOR_gate. You can give any name if you want. Let me write the file name as XOR_gate. Then click on OK. Then click on Finish. Now here, in define module, we need to write the entity name and architecture name. The entity name is XOR_gate, same as the file name. Let it be XOR_gate. Now, architecture name. I am naming this architecture as data flow because I will use data flow modeling. As we have already seen that logic gates can be implemented using data flow modeling with the help of logical operators very easily. Therefore, we will create XOR gate and AND gate using data flow modeling and then combine them together using structural modeling. So, therefore, I am naming this architecture as data flow. Then, here we can see input-output port definitions. Inside this, we need to declare the input and output ports for this XOR gate. Now in the half adder, we are using two input XOR gate. Therefore, I will assign two inputs, let's say X and Y, and one output Z. So, inside the input-output port definitions, inside the port name, I will write signal X, direction in, meaning input port. Then second signal Y, direction in, meaning input port. Then our third signal, our output Z. I will change the direction to the out. Out means output port. Then click on OK. Now, you can find this source file inside this design sources folder. Open this design sources folder and double click on this XOR gate source file. Here we have our VHDL code editor. Let me maximize this. Here we can clearly see that the library and the entity are already declared. First, let me remove these default comments so we can clearly see our VHDL code. Let me delete them. So, this is the VHDL code for the XOR gate after I have deleted all the default comments. Now here we can clearly see that the font size of this VHDL code is very small. If you want, you can increase this font size. For that, go to Tools section, click on Settings. On the left hand side inside Tool Settings, click on Text Editor. Let me click on Text Editor and select Fonts and Colors. Let me select Fonts and Color. Here we can clearly see the font size. I'm increasing the font to 25. You can increase the font as per your wish. Let me change the font size to 25. Then click on OK. Now here we can see that our font size is increased. Now let's see the VHDL code. The code is starting with IEEE library along with the standard logic package from the IEEE library. After library declaration, we are having our entity declaration. And here I have named this entity as XOR underscore gate is port. Now inside this port, we have already declared the input ports X and Y and output port Z, and all of them are of standard logic data type. After port declaration, the entity is ended with the help of the keyword end and the name of the entity XOR underscore gate. Now after entity declaration, we are having our architecture. Architecture named as data flow because we will write the Boolean expression for the XOR gate of entity XOR gate is. Now inside the architecture, after the keyword begin, we will write the Boolean expression for the XOR gate using the keyword or the logical operator XOR operator. So inside the architecture, let me write the Boolean expression. Output Z is assigned X XOR Y semicolon to end the statement. So here I have written the Boolean expression for the XOR gate using the XOR operator. Now for better readability, you can give extra spaces before this Boolean expression. Now similarly, we can write the VHDL code for the AND gate by adding the source file for the AND gate. So here I have written the VHDL code for the AND gate. Starting with the library declaration, then we have entity, and here I have named this entity as AND underscore gate. Inside this entity, I have declared two inputs, P and Q, and one output R, because the half adder uses two input AND gate. After entity, here we are having the architecture named as data flow. As discussed, we will write the Boolean expression for the AND gate inside this architecture of entity AND gate is. Now inside this architecture, we will use the logical operator AND operator to write the Boolean expression for the AND gate. So here I have written output R is assigned P and Q semicolon to end the statement. So we are done with the AND gate VHDL code. So here we have created two separate source files for the XOR gate and for the AND gate. Now we can add another source file to implement the half adder using structural modeling, following the same steps. First, we will use the language VHDL. Then we will give the file name, let's say half underscore adder, and the same name we will use for the entity. Then architecture name will be structural because we are writing the structural modeling code. Then we will declare the input and output ports. The two inputs will be A and B, and two outputs will be sum and carry. After that, the code will look like this. Now, this is the VHDL code for the half adder using structural modeling that I have written. The code starts with library declaration. Then we have our entity declaration. And here I have named this entity as half underscore adder as discussed. Is port. Now, inside this entity, I have declared the input ports A and B and two output ports sum and carry. And all these signals are of standard logic data type. Now, after entity, we can write our architecture. Architecture named as structural because we are writing the structural style code for the half adder of entity name half adder is. Now, I have already explained you in structural modeling architecture, first we will declare the components that we want to use to create half adder. Then we will use port mapping to connect those components. Now, for the half adder, we will use two components, one XOR gate and one AND gate. So, inside the architecture, we will declare the two components using the keyword component and the name of the component or the name of the source file that we want to use. XOR underscore gate, the XOR gate component that we want to use. Now remember, the name of this component XOR underscore gate must be same with the entity name of the source file in order to avoid any error. So component XOR gate. Inside this component, we will declare the input-output ports of the component that we want to use. So for the two input XOR gate, I want to use both inputs X and Y and one output Z. After port declaration, we can end this component using the keyword AND component. Similarly, we can declare the second component, our AND gate, with the keyword component, the name of the component and underscore gate. Inside this component, I have declared the input and output ports that we want to use from the component AND gate. So here P and Q, the input ports, and R, the output port. After port declaration, we can end this component using the keyword AND component. Now, after component declaration, we will use two instances or two copies of these components in order to connect them and create our half adder. So, after the keyword begin, here I have written two instances U1 and U2, or we can say two copies U1 and U2, where U1 is the name of the XOR gate and U2 is the name of the AND gate. Now look at this first line. U1 colon means U1 is assigned for XOR gate port map inside the parenthesis input ports A, B and the output port sum, which means port map. So connect the input ports A and B of the half adder with the input ports X and Y of the XOR gate and connect the output port sum of the half adder with the output port Z of the XOR gate. Similarly, in the second line, U2 is assigned AND gate port map. Connect the input ports A and B of the half adder to the input ports P and Q of the AND gate and connect the output port carry of the half adder to the output port R of the AND gate. So here, this port declaration helps to create our structure of the half adder. Now we can end this architecture using the keyword AND with the name of the architecture structural. So, I hope you understand the component declaration and port mapping and overall VHDL code for the half adder using structural modeling. Now, let's see the schematic diagram generated by Vivado for this structural modeling code. For that, go to RTL analysis, click on Open Elaborated Design and select Schematic. Now, this is our schematic diagram generated by Vivado for the half adder. Here we can see the two numbers that we want to add, A and B, and the two outputs are sum and carry. And here we can see two components, XOR gate named as U1 and AND gate named as U2, which are representing XOR gate and AND gate. And here we can clearly see the input ports X and Y of the XOR gate are directly connected with the inputs A and B. And here we can clearly see the input ports P and Q of the AND gate are directly connected with the input ports A and B. And on the output side, we can clearly see the output of the XOR gate Z is directly connected to the output sum, which means sum is equal to A XOR B. And in the second component, we can clearly see the output R of this AND gate is directly connected to the output carry, which means carry is equal to A and B. So, I hope you understand the schematic diagram generated by Vivado for the structural modeling code of half adder. Now, let's see the simulation waveforms for this half adder code in order to see whether our code is correct or not. For that, go to Simulation, click on Run Simulation and select Run Behavioral Simulation. It will take some time, just wait for few seconds. So, this is our simulation waveform window, and here we can clearly see the two inputs A and B and two outputs sum and carry. In the previous lecture, we have already analyzed the simulation waveform for the behavioral modeling code of the half adder using the fourth combination 1 1. Let me assign the same combination and verify our VHDL code. For that, right click on signal A, select force constant, value radix as binary because we want to use binary number, force value 1, then click on OK. Similarly, we can assign a fixed value 1 for the signal B. For that, right click on signal B, select force constant, value radix as binary and force value as 1, then click on OK. Now let's verify our code. For that, let me run this simulation for 100 nanoseconds. For that, click on Run for 100 nanoseconds. Now here we can clearly see our waveform is generated. Let me maximize this. Let me zoom in further. Here we can clearly see input A is equal to 1 and input B is equal to 1. And for that, sum is 0 and carry is 1. And the same thing we can clearly see in the waveform. For inputs 1 1, sum is 0 and carry is 1, which means our structural modeling code for the half adder is absolutely correct. And I hope you understand the overall process for implementing the half adder using structural modeling. So, I hope you understand the half adder implementation using structural modeling in Vivado. And in the next lecture, we will implement the same circuit of half adder using our third modeling style, data flow modeling. With that, we are done with this lecture. I will see you in the next one. Thank you.